Assalamu alaikum, everyone. I hope you are fine and doing well. Today, this is our second lecture of our series, basically our online series of lecture for the course Introduction to Cryptography. More or less, in this technologically advanced era where the need of securing digital information is unavoidable issue. In this case, modern block cipher, which is the topic of today's lecture, uh, consists of fundamentally confusion as well as permutation or diffusion component that play an important role while constructing any modern block ciphers. In this regard, today we will therefore introduce some basics of modern block ciphers, how our modern block ciphers are fundamentally rely on substitution as well as confusion component, or we can call it non-linear component and linear component of modern block ciphers. In modern block cipher, the only nonlinear component, or in some time we call it as a confusion component, is fundamentally can be achieved through substitution box, which is basically based on affine transformation. In last lecture, I discussed why we have used affine transformation instead of linear transformation in order to construct substitution boxes. No, today our class is about to discuss some modern block ciphers and their component, mainly substitution and permutations. How we can construct them, how one can construct different type of substitution and different types of permutation networks, and how fundamental mathematics like bijectivity, one-to-one, one-to-many, and many-to-one relation can be useful in modern block ciphers. If you have a very basic fundamental knowledge of linear algebra, then you can easily construct a very good modern block ciphers having some very good cryptographic characteristics like good non-linearity, good strict avalanche criteria, bit independent criteria, linear approximation, and as well as differential approximation probabilities. Uh, in case of AES and in case of DES, basically DES is fundamentally based on Feistel cipher, and the AES is based on substitution and permutation cipher, and this is basically the SP network, and the idea of SP networks is given by Cloud Shannon. So let me elaborate these and let us come towards objectives of today's lecture. So I have to just on the spotlight. So okay. Uh, I have to start with my lecture. Let me do something regarding spotlight on that our plan. So the fundamentally today our basically the objectives of our class is about how to distinguish between traditional and modern blocks ciphers, introduce modern block ciphers and discuss their characteristics, to explain why modern block cipher need to be designed as a substitution as well as a permutation network. So I have to go on next slide. To discuss product ciphers and distinguish between two class of product cipher, that is Feistel cipher as well as non-Feistel cipher. Here, the non-Feistel cipher means to say SP networks, substitution and permutation networks. So I'm not going to waste your time anymore. So I have to focus on my lectures. Today our lecture is about modern block ciphers, and block cipher is one of the types of symmetric key cryptography. In symmetric key cryptography, our encryption is mainly based on one key. The key is quite important uh, as we know about Kirchhoff law that explain that it is one of the strongest law in today digitally advanced encryption standards that you can expose your encryption algorithm, but you can say to someone, yes, I'm doing that to encrypt my digital information with, say, with some encryption algorithm, but you don't expose your key. But basically the whole theory of symmetric key cryptography is evolved around basically private key, and we call, sometimes we call symmetric key as a private key because the keys play a quite important role in case of private key or symmetric key, because it is only one key that used at the both end, even in sending end as well as in receiving end. So that is why by the law of Kirchhoff, that don't expose your encryption key. That is why modern block cipher introduces substitution as well as confusion. Basically, confusion make relation between plain and cipher as complex as possible, and diffusion is to spread your add redundancy in your in digital information in order that a passive or active attacker cannot be able to estimate your public so private key. So once again, we must focus on some uh, topic of let me explain the I think I explained a lot about symmetric key like symmetric key. I have explained a lot, but today topics is which will be discussed in this online series of lectures is substitution or transpositions, or we can call it permutation, block cipher as a permutation group. And permutation group, last time in my last lecture we have discussed permutation group. Say S3 is basically permutation of all possible n objects. So component of modern block ciphers, product cipher, two class of product cipher, and attack on block ciphers. So let me start with some basic substitution, and on that let me explain with some basics like let us explain some in let me do it with some let us in this slide, fifth slide, we have modern block ciphers. This modern block cipher, whenever I say block cipher, it means it has some very big n number of bits, and then inside the encryption algorithm we have some chunks. Means to say we convert these n bits into a uh, sub bits. Means to say if I have 128 bits, say in a plain text, I have to convert the 128 bits into eight chunks of 8 bits. Then I have perhaps 8 8 bits. 8 bits. I have 16 blocks of 8 bits. So encryption is performed in chunks, and then we rejoin them at the time of decrypt. Basically, a cipher is placed rejoin from. Let us say, if I can say I have n bits, so here we can convert these n bits into chunks and pass these chunks through our encryption algorithm. Then basically combine all these chunks and we get n bits ciphertext. And the decryption is the reverse procedure. You can give n bits ciphertext to a decryptor, and then you will get n bits plaintext. So with a one key of have a key with k bits. So the idea is to about what I should say. Let me do it. So the idea is to modern block cipher can be designed as act as a substitution cipher or permutation or transpositional cipher. To resist against a brute force attack, a modern block cipher need to be designed as a substitution as well as permutation methods. So let us take one example regarding brute force attacks. Suppose that you have block cipher with N64, means to say your plain text is 64 bits. If there are 10 ones in a ciphertext, how many trial and error tested does Eve? Eve is basically it may be passive, it may be active attacker that is basically watching your communication. It is remain in insecure line of communication. So need to do to recover the plain text from intercepted ciphertext in each of the following case. The cipher is designed as a substitution cipher, and the cipher is defined as a permutation or transpositional ciphers. So, in case of, if you can say this one, like, let me show it some. So, let me explain. If you can have a n bits, 64 bits plain text key size, and you have to recover this. And first case is you have 10 bits once in ciphertext. How many trial and error? In first case, if you used to this to first case, if he has no idea, so if he has no idea, then in that case, he has to apply all possible ways, which is 2 power 64 on 64 bits blocks to find that basically key, or to find that key in this exhaustive search or brute force. We call it as a brute force attack to attack to apply all possible keys. So in second case, Eve knows that there are exactly 10 ones in plain text. Then Eve can launch a exhaustive search attack using only those 64 bits block that have exactly 10 ones. Say you have plain text, also if you have a key of 64 bits, so you know about first, you have knowledge about first or last, or between them 10 bits. So you have to take only that bits and apply your basically brute force attack on that 10 bits in order to get that key. So let us take one example. Show that the model show that the model and the set of permutation table for 3 bits block transposition cipher where the block size is 3 bits. So in that case, we have all possible permutation for 3 bits. If we take it as a, transpositional cipher, so how one can uh, place three object in a distinct way, then we have basically 3 factorial 6 element as shown in figure uh, 5.2. Here you can see, say you have three elements, three objects permutation. It is the basically possible combination for three bits or three bits key. So this is all possible combination of your key. So you have to, if you design a encryption algorithm whose key is based on transpositional cipher with key length is 3 bits. So you have to retrieve this key by applying all possible permutations of three objects, and which is nothing, it is just a symmetry group of three objects or three elements. So some modern component of modern block ciphers. So the modern block ciphers is consist of key substitution cipher, in which key allow only partial mapping from possible input to possible output. So let me explain this with the modern block cipher is basically consists of P box, we call it permutation box as well as substitution box. So P box is nothing, it is just a permutation box parallel the traditional transpositional cipher for character it transposes bits. So if I can say the permutation cipher or columnar or one column, two columnar cipher or Ren fence cipher is one of the example of P boxes or P permutation ciphers. So normally P boxes is of three, basically fall into three types of corresponding to three types of mapping. One is bijective mapping, and one is many to one, and then is many to one to many mapping. In this case, we can say this is a one to one mapping. A number of input and number of output are same, and in that case, we call it straight P box. And in case of compression P box, we call it number of input are larger than number of output. In that case, we can see this. It has basically 5 input, and this input and outputs are just 3. So 4 is remain not being mapped to some element. So in that case, we call it as a compress, or basically it compress the input and you get lesser number of output. Expansion P box, in expansion P box, we call it as an expansion. In that case, number of input is less as compared to number of output. Expanded the your basically input. Here we are showing some possibilities of 3 by 3 P box. Like this is one. It is basically the similar with symmetry group having 3 elements. That is, this is a basically identity element, and this is one is map on 2, and 2 is map on 1, and then 3 is map on 3. So in this case, we have all 6 possibilities for 3 by 3 P box. So, like in that case, we can say, let me explain this with some examples. Let us say this is a one of the straight P box, which is quite useful in DES data encryption standard. This why you call it straight P box, because it can be arranged into a 8 by 8 matrix, and basically these are 64 possible element in this P box, and we call it straight. Why you call it straight? Because 64 bits are mapped on 64, basically 64 element are mapped on 64 elements. So that is why we call it straight P box. And let us take one example. I'm not going to repeat this example. You have to take this example as an homework and kindly perform this uh, example at your home. And if you have any problem, then do ask me regarding this example. So let me forward it towards another type of P boxes, compressible P boxes. A compressible P boxes is a box with n input and m output, where number of output is less as compared to number of input. So same idea is utilized in DES. While we are basically one is expansion P box and one is you can say compression P boxes. So in that case, we call it as compressible P boxes, because here you can see we have 12 element in this row and 12 element in this row, but overall element is basically from 1 to 32. So one can say input element, basically input started from 1 to 32, and the output set is based on map on basically 24 possibilities. So one can say that some of the input might be skipped, or might be basically mapped on more than two output. So in that case, we can say these are just compressible P boxes. And one can say this is a many to one P boxes, because input is larger than output. So same is the case with this also same. So this again expansion P box is a P box with n input and m output, where m is greater than n. In that case, one can say input is less than output. So in that case, we can say this: we have input 12 inputs, and output is map on the here input is 12, but output is larger as compared to input. So one can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So one can say if you have 12 input, and the output will be 16 element. So in that case, our mapping will be one to many mapping. So if I can sum up these P boxes, so P boxes boxes basically classified into three major classes. One is straight, second one is compressible, and third one is expansible. So in case of straight P boxes, it is always invertible, but compressible and expansion P boxes are not compressible, basically not invertible. So at some time we need invertible P boxes. So there's a comment that I have discussed in last slide. So let us take one example. In figure 5.6, show how to invert a permutation table represented as one-dimensional table. So let us take one of the table that is placed on one-dimensional array 634521. So I place the indices over here to all of my element which are originally placed over here. So the I correspond index 1 to 6, then index 2 through or 2 to 3, then 3 to 4, and then same on I place 6 in the index 6 to 1. So I swap the component and indices like I place these component on upper row, and then I put these this row at second place like this. I just swap this element, or I put this one indices in upper row, and then element in lower row. So I sort it out on basis of indices like my first uh, sort based on indices. So one indices is basically 6, and index 2 is like one can say this one. And then 2, mm, I place 1, 2, 3, 4, 5, 6. Then basically 1 is 6, and then 5, 2 is map on 5, and then 2 is 3. If I can say this 3, then this will be map on 2, and this you can say in same manner one can say 1 is map on 6. So I place indices in the down row, and the corresponding element in a upper row. So at the end, the invertible table will be 6, 5, 2, 3, 4, 1, which is basically the inverse of this one-dimensional permutation table. So these are some geometrical representation of compression and expansion p box. Are why these are not invertible. So let us look at this figure 5.7. Here you can see there are three input, and these are map on two output. So input 2 is lost. So while inverting this, then two we have three input. So inverse is not possible in this case, because 2 will remain. There will be no mapping corresponding to 2. So output 2 cannot be assigned a definite value. In that case, inverse is not possible. So once again, we are taking another examples of expansion P boxes, like where the input is less as compared to output. In that case, one input is mapped on two further output. And that same is the case with one is mapped on one, and similarly one is mapped on two, and two is mapped over three. So one is map on two output. So in that case, whenever we are inverting our that type of expansion P box, then there will be no two element correspond to one element. In that case, even inverse is not possible. So let me once again come up with the idea of substitution boxes. And as we have discussed the uh, types of P boxes. Similarly, we discussed types of S boxes that are basically bijective S boxes, straight S boxes. It can be compressible S boxes. It can be expansible or expansion types of S boxes. Same is the case that are also correspond to input or output. When number of input and output are same, then we can say these are bijective or straight S boxes. When number of input is larger than number of output, that in that case we can call it compressible S boxes. As compressible S boxes are also utilized in DE as data encryption standard, where number of input are 6 and number of output are 4, as compared to straight S boxes, and straight S boxes are utilized in AES, Advanced Encryption Standard. So S boxes can be thought of as a miniature substitution cipher. So if I can say in a separately, if I can say, not just talking about modern cipher, that then substitution boxes is just like a hill cipher that substitute something to some other element. So an S box is an M cross N substitution unit where M and N are not necessarily equal or same. So let me give you one example how one can construct substitution boxes with 3 input and 2 outputs. So this is the transformation from Z23 to Z23. These are 3 tuples, that is, and its base is binary, and this is again 2 tuples and its base is binary. So I can take one linear transformation, A x is equal to x. This is a 3 cross 1 tuple, and this is a 3 cross 1 tuple, and the matrix is of order 2 cross 3. In this case, input is 3 and output will be 2. So I take these output as a function of input. Say y1 is x1 XOR x2 XOR x3, and y2 is x1. In that case, S box is linear because A1, A2, 1, 1, A1, 2, A1, 3 are 1, and A2, 2, A2, 3 are 0. In that case, basically from this even from this transformation, one can realize this is a linear transformation, and corresponding to linear transformation, we have always a linear substitution boxes. So this is an input and this is output, and this is a 2 cross 3 matrix. So x1, x2 are input. So in that case, if we plug all the possibilities in to 0 to 3, and it has basically 8 possibilities, and we plug all these possibilities over here, and we just get 4 possibilities. In that case, our substitution boxes will be 3 by 2. So take another substitution boxes where input is 3 and output is again 2. Also take one expression y1 and y2, which are fundamentally based upon 3 input. Once again, x1, x2, x1, x2. These are, from this term and this term, we can say this substitution boxes is has no linear relation between input and output. So one can say these are not just a linear substitution boxes, these are non-linear substitution boxes. So let us take one example, substitution boxes of size 3 by 2, means to say it take 3 input and the output will be 2. So how you can say these are basically input, and this is also input, and the element inside this table is basically the your output. So if I can map, let us say I take input as a 0 and 1, 0, 0, 1. It's a 3 input. Basically, this substitution box take 3 input and map on 2. So first element basically tell you the row, and last to tell you about column. So 0 rows and 1 0 column. So the output will be 0 1. If I can say I take another 3 input, say 1 0 1 0 1. So 1 is basically your row and 0 1 is your column. So in that case, your output will be 0 0 0 0. It's basically the substitution boxes from 3 input to 2 input. So let us take S boxes may or may not be invertible. It's clear from my discussion when substitution topic of substitution boxes are just start, and I have discussed the invertibility of substitution boxes. So let us take another example in figure 5.8. In this, you can clearly see these These table basically clearly reflect that we have three input, and these are also map on three output. So in that case, our substitution boxes are bijective. In that, you can see this is, say, if this is an input 0, 0, 1. So 0 is your, this first element tell you about row, and last two tell you about column. So 0 rows and 0, 1 column. That is basically this element. So this will be the 1, 0, 0, 1. This will be obvious. Similarly, you can take any possible three input plain text and pass through these three by three substitution box, and you will definitely get your ciphertext. And whenever we are just passing our information through substitution box, they are just behave like substitution cipher. And you know, cipher are of further two or more than two classes: mono, polyalphabetical cipher, and like this one. So let us take one XOR operation, an important component in modern block cipher. We usually used to with this XOR operation. That XOR operation basically you have input X and you XOR with K and you get Y as a output, or we can call it in cryptography, we call it ciphertext. So to get back your plain text, we just XOR Y with K and you will get back X, which is your plain text. So invertibility of XOR operation is can be clearly verified through figure 5.9. Circular shift. The idea why we are doing this circular shift or shift and number of operation which we are doing in this particular lecture. Uh, Basically, we are doing all these because we want to basically make ourselves ready for to modern block ciphers, how we can realize their computations, their basic fundamental steps, how they perform, how they, when you just pass any information through these modern block cipher, actually what they did with digital information means to say bits. So circular shift, basically there are two types of shift. One is left or one is right shift. Uh, it can be related with clockwise shifting or anti-clockwise shifting. In the first case, before we shifting, we just take 8 bits. You can see I just use blue color to just color these last three bits with blue, and these right-handed bits, say B2, B1, B0 with green color. So I just perform anti-clockwise rotation or anti-clockwise shifting. So you can say if I rotate like this one, like I place this one and rotate anti-clockwise like this. So in this way, like this one, like this red arrow. So all these 7, 6, 5 will be placed at the end of these basically byte, which is consists of 8 bits. So I have this one and we call it left shift. And let me clarify with this example how we can form a right shift. So this is a basically clockwise shifting. So I can just shift these 3 bits to the first position. So in that case, B2, B1, B0, the last 3 bits will be placed at the first three positions. So in that case, we can say we perform left shift with 3 bits. So dear student, these left or right shift are basic component of diffusion and DES as well as in AES. Basically, AES has four transformation: substitution, shift row, mixed column, add round one key. The substitution sub-byte transformation is mainly related with substitution, cipher, and shift row is basically based on this circular shift. Here we can say this is one of the circular shift. So, uh, so, uh, so we must start with another one, swapping. So this is, you know what, swapping. We have to swap this. Like I have these 8 bits, 1 byte. So I just make them, divide them into two blocks. Say first block and second block. Then swap these blocks. The chunks of 4 bits swap to these left bits to right and right one to left. So I get another one. I don't call it encryption. In case of decryption, we have to perform reverse operations. So place this, shift this one to left, right one to left, and left one to right. So we get back our original byte, which is consists of 8 bits. So we have another basic term of splitting or combining. Two other operations found in this some block ciphers are split and combining. Split and combining operation on 8 bits would say you have 8 bits, so you have to divide them in equal bits length and then divide it equal bits. So you have two chunks. So in combining, you just combine them and get back your original plain text. So this is the same idea. Why we call it like product cipher? So in previous slides, we just discussed each and every component separately, substitution as well as permutation boxes separately. But after the idea of Cloud Shannon, that you can design modern block ciphers with the help of substitution as well as permutation. So in one block cipher, we must have substitution as well as permutations. So we call it as a product cipher. And the product cipher is consists of substitution as well as confusion. So permutation basically give the idea of diffusion, and diffusion of the idea of diffusion is to hide relation between cipher text and plain text. Uh, and diffusion is related with how one can hide the relation between ciphertext and plain text in order to provide the safety to your plain text when it passes through insecure line of communication. Confusion is basically created or can be designed through substitution boxes. The idea of confusion is to hide the relation between cipher and key. Confusion hide relation between ciphertext and key. My question, why we have to make relation between cipher and key as complex as possible? The important component in the answer to this question is it's quite important component of symmetric key encryption algorithm that key should not be shared. By Kirchhoff law of information security, why we can expose our encryption algorithm, but we don't compromise on sharing our encryption key or its possible linear combinations, or we should not share this with anyone, or it cannot be recovered from the possible combination of plain and ciphertext, or you cannot create original key with the help of linear relation between ciphertext and key. So that is why you can expose your encryption algorithm, but you cannot expose your key, because the theory of block ciphers are mainly based on encryption key, because there is only one key which is utilized at the time of encryption as well as at the time of decryption at receiving end. So another component of the modern block ciphers are round. Diffusion and confusion can be achieved using iterative block cipher, where each iteration is the combination of substitution and permutation and number of other components. So this is one of the block ciphers diagram of what you call it as a product block cipher that can basically use substitution as well as permutation and number of rounds. On each round, there is a one key for every round, and the key mixer is nothing. It is just a XOR operation. So in every step, we have substitution as well as permutation networks. So it's a diffusion and confusion in a block cipher. So you have 8 bits block cipher and you XOR key with 8 bits, and this XOR, by XORing this one, you pass this with say some substitution boxes that you generate 7 and 8 instead of you have 8 inputs and you just 7 and 8 are there. So you just use then permutation, and then middle text you will get 2 and 4. Then using substitution, multiple substitution, you will get, and multiple permutation you will get ciphertext. So modern block ciphers is fundamentally divided into two classes in a major sense. First is Feistel cipher and other one is non-Feistel cipher. Whenever we are talking about non-Feistel, means to say SP network, and there are Feistel cipher that you basically based on Lucifer cipher. That was the while you discussing Feistel cipher, inside Feistel cipher, the Lucifer cipher is utilized generally, and it may be one or it may be more than one network of that is based on Lucifer cipher can be utilized. The famous one, Feistel cipher, which is based on Lucifer cipher, is DES, data encryption standard, and that was developed in 1975 by IBA, or and with the close what you call the call of NIST, National Institute of Standard Technology. So let me explain this Feistel cipher. Feistel cipher designs are very intelligent because it's here in Feistel cipher, the one of the facility in Feistel cipher is self-invertibility, means to say at sending as well as in receiving end, who don't need inverse substitution boxes. So you just utilize the same algorithm for decrypting your encrypted message at the end. But again, the that also depend the encryption Feistel cipher is depend upon your key. But in case of DS, where key length is 64, which is possible prone to a brute force attack. So prone, I mean to say it is exposed to brute force attack. 2 power 64 can be achieved through your modern computational capability. Let us explain. It has some Feistel cipher can be classified into further three classes, that is self-invertible, invertible, and non-invertible. Then we have thought Feistel cipher as a, so you have a P1, so you have some function, expansion function. So inside this is basically a black box, and you just that operate on K, and you mix plain text, basically XOR or mix up plain text with this function, and you'll get C1. And the if you get back your for decryption, you have to perform reverse operation. The basically diffusion hide the relation between cipher and this is nothing. It is just a Feistel cipher is nothing. It is just doing permutation in your block ciphers. Let us take one example, one very trivial example. So you have a plain and ciphertext are of each 4 bits long and key is 3 bits long. Assume that function take the first and third bit of the key. So your plain text is consists of 4 bits. That function take first and third bit of key, interpret these two bit as a decimal, square the number, and interpret the result as a 4-bit binary pattern. Show the result of encryption and decryption if the original plain text is 0, 1, 1, and its key is 1. So we have to take first and third element of key first, and that is 1, and this one I take it 1 1 and I convert this it into binary to decimal, which is 3 equivalent to 3. Then I square this number which I get from the binary to decimal, which is equivalent to 9, and then I place this 9, convert this 9 and back to binary. Then I get 4-bit binary 1001. Then I perform encryption like XORing 1. C equal to P XOR f of k, and I call it this as a f of k. Basically, I perform some operation on key, and then I get another element k. So f of k, I perform some operation on k. That is, I take one and first and last element of this binary key, and then uh, concatenate these keys, basically combine these first and last bit of the key and convert this 1 1 into from binary to decimal. I get 3, and then I square this 3, which is 9, and then I put 9 put basically convert 9 from decimal to binary, then I get this element. So this is f of the whole operation, we call it f of k, and that's in 100. So the my plain text is 0111, which is this one, and I just XOR this with my this function f of k. I get 1110. Then I get back plain text. This is the ciphertext, and C with XOR with f of k. Then I get back my plain text, which is this one. So this f of k from this last slide, this f of k can be achieved through you have to perform certain operation on your key. So I just explain this with the help of example 5.12. So this more or less same as we discussed in our previous lecture, previous slide. Sorry. So final design of Feistel cipher, basically it consists of if you have say n bits, and you just split it into left or rightmost bits, leftmost block and rightmost block, and then pass through this black box, which is f of r1k, and then you get XOR this f of r1k with uh, with some what I say with L1, this L1, then we call it L2, and then join this as it is this with R2. and we got L2 R2 and who have performed reverse procedure in order to get back our plain text. So in that case, we can say the Feistel cipher, we can perform this these operations repeatedly in a number of rounds. So we get a number of left or rightmost bits. Like this is first round, this is basically mixing with XOR, then this is swapping, this is permutation. Then we perform in second step, we take this R2 and perform some F with in some second round key. As I told you, that in Feistel as well as permutation cipher, we have key for each round. So in that case, we have key for first round, we have key for second round, and we have key for third, fourth, and so on, and round. So in this is if you want to get back your plain text, so you have to perform a reverse procedure in a reverse order in order to get back your plain text. So non-Feistel cipher uses only invertible component. A component in encryption cipher has corresponding component in decryption ciphers. So these are, in that case, we can say the AES is based on non-Feistel ciphers. Attacks on traditional ciphers can also be used on modern block cipher, but today block ciphers resist most of the attacks discussed in our previous lectures. So I must thank you all by bearing me for such a long time. This material are basically taken from the book, the title Cryptography and Network Security by Rosen. And thank you all for bearing me for such a long time. And if you have any question, do ask me. And moreover, uh, we will discuss in our next lecture about DES, which is again based on Feistel cipher and AES. Till then, Allah Hafiz and stay at home and do prayer from Allah. May Allah bless us, all of us as a nation, and in order to cope with this uh, pandemic emergency. Allah Hafiz, and may Allah bless you all.